Question 4 invites us to look at these three compounds and put them in order of increasing boiling point. So the first thing to pick up on is that they're all very similarly sized molecules. These two indeed are structural isomers. This one you can see looks very similar to that one, but it just has an extra CH3 instead of an OH. And as we already discussed in an earlier question, that means they actually have the same number of electrons. So we're comparing very similar things here, but the big difference is going to be that these two can form hydrogen bonds because of the OH groups, whereas this one can't. And remember that hydrogen bonds make all the difference because they're much stronger than other intermolecular forces. So if you have to break them in order to boil it, it's going to take a lot more energy, and that's going to make the boiling point higher. So straight away we can say that this one is going to have the lowest boiling point, which is that compound. So that's going to be the lowest. And then we'll worry about the other two in a minute. But we've got to make sure that we've explained fully why that's the lowest, because it can only form induced dipole-dipole forces. Remember, it's important not just to say it can't form hydrogen bonds, you should say what it can do. So induced dipole-dipole forces, which are weaker than the hydrogen bonds. The other two compounds can form. So it takes less energy to break them. But that last bit's really important. It's not enough just to say they're weaker, you've got to explain why that matters. Because they're weaker, it takes less energy to break them when it boils. Okay, so that's dealt with that one. So now we've got to decide between the two alcohols. And the important issue here is that just because they can form hydrogen bonds, it doesn't mean that the induced dipole-dipole forces they form as well, it doesn't mean that they don't matter. It's just that the hydrogen bonds are much stronger, so they make the difference compared to other compounds that can't do that. But since these both can form hydrogen bonds, the difference between them is going to lie in what the rest of the molecule can do. And what the rest of the molecule can do is form induced dipole-dipole forces. So what this comes down to is remembering what difference branching makes, which we learnt about with alkanes, but it applies just as much here. Oh dear. Right. So remember that when you have a branch in a molecule, it decreases the surface area available for contact with other molecules, because basically it gets very crowded around the branch. It means other molecules can't get as close around that part of the molecule, so there's less surface area in contact with other molecules, therefore there are fewer induced dipole-dipole forces you have to break, and that therefore requires less energy and decreases the boiling point. So when you have structural isomers, the branched ones, the more branched they are, the lower the boiling point compared to the unbranched one. So that's going to give us our order. Although this is going to be much higher boiling point than that, it's going to be lower than this one because of that difference. So we can complete our order and say, right, this is going to be the one in the middle. And then the straight chain one is going to be the highest. And again, we've got to give our explanation for that, comparing these two. So it's the idea that branching decreases the surface area in contact with other molecules. Don't just say decreases the surface area, because they may say, what's that got to do with it? So decreases the surface area in contact with other molecules. It's important you get that the right way around, and the thing to do is to think about it and realise that it's going to be difficult for other molecules to get close because it's already crowded around the branch. And that's the way to think about why the contact surface area is lower. So decreases contact surface area with other molecules, so fewer induced dipole-dipole forces need to be broken when it boils. Compared to a straight chain compound. Which in turn means that less energy is needed to boil it. Okay, so it's all the standard stuff, but it's about recognising that hydrogen bonds make the difference compared to other molecules that can't make hydrogen bonds, but that doesn't mean that the other intermolecular forces, the induced dipole-dipole forces, it doesn't mean that they don't matter. And so when you're considering branching, you talk about those exactly the same as if it were an alkane question. Question 5 then is about making alcohols from alkenes. Which was one of the reactions you already learnt when we looked at alkene chemistry. So remember, this involves whatever alkene you've got, so whatever the groups attached there, the reaction is always the same, that you react with steam. If you think of a water molecule in steam like that as having an H at one end and an OH at the other end, remember all that happens in terms of the outcome, this isn't the mechanism but this is the outcome, is that you break the double bond down to a single bond, you break the bond between the H and the OH, and you form two new bonds like that. So you add H to one end of where the double bond was and OH to the other end, and that's an example of an electrophilic addition which you already know about. So in this case you can see that this is a nice simple example to start with, in the sense that the molecule is symmetrical. So you don't have this worry about will it add this way round or will it add this way round, because it doesn't make any difference. Because the molecule is symmetrical, you're going to get the same product whichever way round it adds. And so that's very straightforward. So it's going to follow that pattern we saw a minute ago. Break the pi bond here, break the H to OH bond there, and form two new bonds there and there. So the reaction is going to be there, plus H2O, and then all of these atoms are still here, because remember it's an addition reaction, which means you're not replacing any of the existing atoms, you're just adding new ones on. So all of these atoms that were there in the beginning are still there, but we've just added the H and the OH like that, and that's the only product. Okay, so that's the addition reaction there. So here we're going to get the same thing. We're going to add H and OH across this bond, but this time you do have a question of which way round will it mainly go. Will it go that way, so the H adds to this end and the OH adds to that end, or will it add mainly that way round? So we can write the equation with alternative products, but then we're going to have to consider which one will be the major one. So we've got that plus water will give us either one product or the other product. I'll just put or in there to make it clear we don't get both of them, or at least we would get a mixture of both of them, but any single molecule has to do one or the other. And as I say, just a case of either we can stick the OH at this end, which would give us this product, or we can stick the OH at that end, which would give us that product. Okay, so those are the two possibilities, but then we have to describe which is the major one. So that's about the Markovnikov issue. It's about remembering that when you think about the mechanism of the reaction, it goes via a carbocation intermediate, that positively charged intermediate. If you don't remember that, you need to look back at the alkene chemistry, because that's a mechanism you need to know all about. So this one would be formed via a carbocation that basically has a positive charge where the OH ends up. So it would be formed via that carbocation has a positive charge there, because remember OH minus is formed in the intermediate stage, which then just bonds on like that. And that is a tertiary carbocation, because the carbon with the positive charge has 3 other carbons attached. Okay, so that product would be formed via a tertiary carbocation. This one is formed via a carbocation that looks like this. Okay, because again, where the OH ends up, there would have been a positive charge in the intermediate, and you can see the carbon with the positive charge has only 1 other carbon attached to it. So this is a primary carbocation. And then you just have to remember the story, which is that the more carbons you have attached to the C+, the more stable it is. In other words, tertiary carbocations are the most stable, then secondary, then primary. So this is the more stable of the 2 carbocations. If it's more stable, it means it will be formed more easily, and therefore it will lead to the main product, the major product of the reaction. So that's going to be the major product. Okay, so we can just summarize that at the bottom by saying that this compound, okay, which is that one, is the major product, because it is formed via, and it's very important you get the wording here, because people say things like, oh, because it is a tertiary carbocation. I mean, it's not a carbocation, it's formed via a tertiary carbocation. So you've got to get the wording right here. Formed via a tertiary carbocation, which is more stable so more easily formed than the alternative primary carbocation. Okay, so again, that's quite a complicated story, but it's always the same issue. So if you learn the Markovnikov thing, learn the wording, then the questions are actually easy. So you just write down what the alternative carbocations are, and you classify them as primary, secondary or tertiary, and then just remember how it goes. The tertiary one is going to be the most stable, so if you've got one of those, that's to its advantage. It means it will form more easily and therefore will lead to the major product. So you've got to practice answering those questions sort of clearly and fully. In part 3 we have a diene, so 2 alkene groups, both of which can add H2O across the double bond when they react with steam, when there's a phosphoric acid catalyst. It's written out here as a structural formula, which is fine if you're comfortable with those, but I don't like them. I would be inclined to redraw that first of all as a skeletal formula, just because it's going to then make it easier to follow through the rest of the question. But you don't have to do that. You can stick with that format if you prefer. But if we draw that out as a skeletal formula, we get that. Okay, I haven't worried about EZ issues here because that's all going to go away once the double bond has gone anyway. So I've drawn the EE isomer, but it wouldn't make any difference if you had one of the other ones there. So that's our starting point. And I think the easiest way to do this is to just consider the alkene groups reacting one at a time. So you can say, right, let's start with this alkene group and say that you've got the usual problem that it could add either this way round or this way round across the double bond. So that's straight away going to give you two different possibilities if just that group reacts. So we could either get the OH there and the hydrogen at this end, or we could get the other way round, so the OH goes here and the hydrogen goes that end. Okay, and that double bond has yet to come into play. So once that's reacted, we can then get this one to react as well. And again, we've got two possibilities, because here you can add hydrogen to this end and OH to that end, or you could do it the other way round. So that could give you this compound. Okay, if we had the OH to that end and the hydrogen to here, or if it adds the other way around. Or we could add the OH to this end, which would give you that product. So you can see here we've got heptan 2,6 diol, whereas here we've got the 2,5 diol, so they're different compounds. And we can do the same thing here and realise that again, if that one reacts first, you can get two possibilities here. So the OH could go at this end, which would give you this product, or it could go at this end, which would give you this product. So you might be tempted to say, right, there we go, 4 possible products. But actually, when you look carefully, you realise that this and this are the same thing. Okay, they're drawn the other way around, but if you imagine picking this molecule up and flipping it over like that, it's actually exactly the same as this one. If you have trouble visualizing that, one way to convince yourself that it's true is do the sort of naming thing. In other words, count the carbons and actually number the carbons where the OH is attached. So you can see here, if we start from the end closest to the OH, you've got 1 at carbon 2, and then 3, 4, 5. So this is the 2,5 isomer. This one, again, you start numbering from the end closest to the OH. So that's carbon 2, and again it's 1, 2, 3, 4, 5. So these two are both 2,5. So it's two different ways of drawing the same thing. Okay, so don't get fooled by that. So that's one isomer, which is 2,5. This one is 2,6, and this one is 3,4. So you've got 3 possible products in that reaction. Question 6 then is another way of making alcohols, which this time is again a reaction. You know, it's a substitution reaction this time for a haloalkane, in which we can replace the halogen with an OH group in a nucleophilic substitution reaction. So again, this is something you should know all about from the haloalkane stuff that we've already done. So again, the equation is really simple because it's a straight swap. Carbon chain stays the same. Where the bromine was, the OH ends up. So that's 2-bromopentane, chain of 5 with the bromine on the second carbon, and it's going to still have the chain of 5 with the substituent at the second carbon, but that's now going to be OH instead. And you can see, just to balance the equation, that means that NaBr will be the other product. So that's the equation. And then it asks us to name and write down the mechanism for this reaction, which again you've already learnt about. So the key to it, remember, is the polarity of that bond. Bromine is more electronegative than carbon, which means it's pulling electron density that way towards itself, so you get delta negative bromine, delta positive carbon. And it's that delta positive carbon that's the weak point in the molecule, because that makes it vulnerable to attack by things that have lone pairs, which remember we call nucleophiles. And OH minus is a good nucleophile. So that's going to be doing the attacking, and we draw on one of the oxygen's lone pairs. It has 3 in an OH minus ion, but it only uses one of them, so we only mark the one on there. And you can see what's going to be happen, that negatively charged ion is going to be attracted in towards the delta positive charge, and when it gets close enough, a bond's going to start to form where that lone pair is used to form the shared pair with the carbon. And we show that, remember, with a curly arrow that looks like this, which must point from the lone pair to the carbon that's being attacked, must point directly at the atom that's being attacked. And what we also know by now is that that can't be the only thing that happens, because if that happened and nothing else did, that carbon would end up with 5 bonds, and that's not possible. So if one pair of electrons is coming in, it's going to push another pair away, and the one that's going to be pushed away is this one, the bonded pair between carbon and bromine, because that can then become a lone pair on bromine, allowing the bromine to leave as Br minus, and we know that bromine's quite happy as a negative ion, so that's a reasonable thing to happen. And this is a really simple mechanism, because that's it. That's the whole story. So you just then complete that by saying, right, okay, all of this carbon chain is the same. I mean, you can draw it like this, which looks a bit weird, but if you want to sort of preserve the position in space, there's no reason you shouldn't draw it like that. But you don't have to. And the Br minus ion is formed. You should show that lone pair. Again, this bromide ion actually has 4 electron pairs, 4 lone pairs in its outer shell, but you show this one because you're showing what the fate of that bonded pair was. The result of that curly arrow there is that what was a shared pair has now become a lone pair on bromine. So you show that like that. And that's it. That's the whole story. And it's called nucleophilic substitution. Okay, and you need to know that term. So substitution for obvious reasons, because you've substituted OH in place of the Br. Nucleophilic, remember, a nucleophile is an electron pair donor. Okay, that's what the OH minus ion is doing, is donating an electron pair to form the new bond. So we say that's an electron pair donor, and the word for that in organic chemistry is a nucleophile. Okay, so that's the explanation for calling the mechanism nucleophilic substitution. Part C is just taking you back to one of the key things you learnt when we did haloalkanes, which was to ask you to compare the rate of the reaction of 2 different haloalkanes in a nucleophilic substitution. So these are the 2 we're being asked about, 2-bromopentane, 2-chloropentane, and what you need to remember is that this one will be faster, first of all. Okay, so as you go down the group 7 elements, in this context, in a haloalkane, the reactivity increases. So chloroalkanes react quite slowly in nucleophilic substitution, bromo ones are faster, iodo ones are faster still. So that's the answer as to which one reacts faster, and the explanation has to do with the strength of the carbon to bromine bond compared to the carbon to chlorine bond. Okay, so that's faster because the CBr bond is weaker than the CCl bond. You could, if you like, put that in terms of bond enthalpy, which would, I suppose, be a slightly more rigorous way of saying the same thing. So you could say CBr has a lower bond enthalpy than CCl. And that may be enough, but I think you should really spell out a bit more, why does that matter? Why does the bond enthalpy matter? And of course the point is that there's an activation energy, which is something we'll talk about more when we get onto rates of reaction, but you have to put some energy in to start breaking bonds in the existing compound before you can form new ones. And the stronger those bonds are, the more energy you have to put in to make that happen, and the less likely that makes it that a reaction will actually happen when two molecules meet. But as I say, that's something we'll talk about much more later on, but I think it's just worth adding to that because the CBr bond is weaker, this means that the activation energy is lower for the bromoalkane reaction. Okay, so make sure you learn that story about the reactivity of haloalkanes. The other thing you need to know about, which it didn't ask you here, is the experiment that you used to investigate it. So if you've forgotten about that, that's something that's worth looking back at as well.